Okay, so first of all, thanks so much for coming. My name is Ben Mark. I'm the backend team leader of Neuro. Also in the audience, we have Dennis, the front-end team leader, which contributed a lot to this platform. Thank you very much, Dennis. So, thank you. Yeah, I'm searching for this. Okay. So today we're going to expose a lot about what is Neuro and how Neuro is the next generation of the virtual classroom. Um, Also, we're going to just a second. I hope this will work. Oh, there we go. Can we go? Can we get this higher? Oh, okay. Um, Actually, I prefer that. So this is the highest. No, it's all people's problem. Yeah. No, I prefer this. Okay, so let's start all over. We're going to discuss today a lot about what is Neuro and how Neuro is the next generation of virtual online education. Neuro is practically a real-time platform for strictly teaching. Um, Basically, Neuro is a online web-based virtual platform designed strictly for education. Unlike other vendors that are based for video conferencing, Neuro is designed strictly for teaching. In Neuro, you don't need to install or download any client. Thanks to WebRTC, we can just access a link and connect to the class. This is a selected list of our customers, which we are proud to serve on a daily basis. Also, because of this, because of choosing Neuro as a platform, you can also see that we are exposing a rich tool set, which is basically our extension to a physical classroom. Basically, with our toolset, we also have the most basic feature that has inside the classroom, which is the whiteboard. But not only that students can also write down on the whiteboard, teachers can also control who's going to write where. Permissions, you can also raise your hand by a click of a button. And basically, you can also view and remove the whiteboard depending on your wish. Also, we have the breakout feature, which is practically dividing the main class to a subclass to working groups. This is very effective for a large scaled class. Also, we have a screen share feature, which allows us to basically share our screens, share our content directly into the virtual class. Also, we have the quiz option, which is simply verifying student understanding inside the class. And our microphone is and our file management system, which is basically allowing us to also share files, PDFs, docs, you name it. We can also share presentations, Keynote, PowerPoint, anything, and also we can also share a YouTube video into the class. So why did we pick Janus? Basically, the main reason that we picked Janus is for its C implementation. Also, we picked Janus because of its amazing community. It's very hot here. And also, we just a second. That's How do you mark it? I can't see nothing. Okay, so we have a small technical issue with the presentation here. But eventually, every Janus release that is out there, we're testing it, very extremely heavily testing that on load also, and checking for every issue that is not registered inside the GitHub issue, the issue list. And also, we're proud to say that Janus 073 up to 073 is extremely stable. Sorry, guys. The air conditioner here is something. How did we integrate Janus with our platform? So obviously, we integrated Janus with the video room plugin like everybody else did. Only that we also have a cascading feature for every stream that is integrated inside the classroom. Eventually, we are supporting up to 1,000 participants inside an online webinar. Not only that, we're supporting up to 25 live participants inside the class. So whenever a webinar kicks in and we are in need to support thousands of streams inside that webinar, we're simply duplicating that stream into other media servers. Also, we're doing this to give a lower latency to high latency viewers. For example, I'm a Chinese viewer, and I'm viewing my stream from a published stream from the United States. So if my latency is too high, basically Neuro is going to duplicate that stream and raise up a media server right in China, and it's going to duplicate that stream right over there thanks to the RTP forwarding mechanism that Janus provides. We are also cascading a stream once a Janus reaches its threshold, which is the main reason why we are even doing that. After load testing Janus quite a lot, we realized that Janus has, like any other server, has a threshold on different EC2 machines or different cloud machines. Those thresholds differ by different cloud machine, as you know. And basically, we are also monitoring every Janus worldwide. And for all of this backend service, we're also providing a gateway for our customers to simply implement Neuro as a service. This gateway exposes the rich tool set of Neuro, but not only that, it also provides an easy and slight mean to simply integrate Neuro into your product. You can also get use of the entire streaming mechanism that we have, which is a lot of wrapping up edge cases and the cascading feature and plenty more. And you can simply implement. Which brings me a bit into our architecture, the high-level architecture. First of all, we decided to become a cloud-agnostic platform. This is for the main reason, that our customers are requiring our product to be on-premise. And for that, we had to basically create a customized auto-scale service and also all sorts of cloud providing services. And eventually, we decided to just use only the essential components of every cloud provider. This allows us to eventually be deployed on Azure or on Amazon or even in your own company's servers. Also, we have a the auto scaling is also in charge to raise the Janus instances, the signaling servers, and also the turn servers, and also the regional monitoring servers. And as you know, every server has a threshold, and we have a huge cluster of monitoring service in every region that basically verifies that threshold there all the time. We are communicating with the entire architecture with Redis channels, And our architecture itself is designed to be a microservice architecture, which we're going to talk about that pretty soon. And this leads me to the crown jewel of our technology, which is the project Reactor. We decided to go to a reactive implementation after plenty of POCs, plenty of thoughts, and this reactive approach gave us plenty of advantages over other technologies. The main advantage that it gave us is to harness the maximum use of all the cores in every machine. Also, this reactive approach is extremely fast, extremely performable. Also, the code is extremely readable, and most of all, the reactive approach gives us the allowance to handle back pressures that are reported from each server in runtime. And as I'm going into deep with a signaling server approach, we know that from the Janus demos we can interact with Janus from the browser. Some of you also use a signaling server. Well, we are using a signaling server too. Only this signaling server is a reactive implementation, which also gave us a fantastic number of 300,000 send event per second, thanks to the reactive approach. The signaling server here is also stateless, thanks to Redis. And we are in a module composition architecture, which means we are not only reusing code, we're also reusing modules. So just like Janus is a plugin module architecture, our server is basically a module composition architecture, thanks to a jar composition that Java provides us with Gradle. And right after that, we can also get into a bit into deep to the backend architecture. So I can't every time I move to the screen, you guys can hear me. On the right hand side, we can see the microservices modules themselves. Those microservice modules are the exact components that we're composing together and building them to different services. As you can see, Redis channels is in the center. On the bottom, we have the Janus servers scaled out through the entire world key regions to be exact. Also, we have turn servers deployed separately from the Janus instances. And on the left, we can see the auto-scaling service, which is our custom-made service. It's pretty robust. Took us a lot of time to implement correctly. To be also abstract to handle every cloud provider, and also to communicate with the services for back pressure, for threshold, for anything, failover whatsoever. It's important to note that the autoscale, like the monitoring service, its failover approach is basically a master slave. So every time, and every minute of the day, there is another slave autoscale service that also is able to scale out with more slaves. But it's also fixing up any failure of any master. I forgot to say from the last presentation that we also have a load testing cloud network that we created to simply raise up machines as we desire, to simply imitate load on the system. So eventually, when you build such a system, you want to test it in an end-to-end way. Of course, we're going to get deep down into testing and how we did that shortly after. But as you can see here, Januses are located everywhere. So thanks to our customers and thanks to the usage, we're also happy to say that even in this region and any other region, there are plenty of Janus everywhere. We are scaling them out in a Docker container approach on a large cloud machine. Once you raise a cloud machine, it takes time. It takes like a minute or a minute and something. And we don't like that time that it takes. So we're basically creating a large instance up to 16 cores and basically deploying in it our Docker instances. Also, this applies for Janus, for turn servers, for signaling servers, and for all other microservice components. And speaking of which, this is our Janus monitoring service itself. Eventually, this service is responsible of simply decorating every instance with its own status, with its own different status. It's also a scaled. This service is deployed in every region, obviously, and thanks to this service, we're not reaching any threshold of any Janus or any signaling server or any other different server that we have. It's important to say that the turn servers that we're using with CodeTurn, their threshold is much more higher, but their job is less hard than a media server or a WebSocket server. And this brings me next to our load testing infrastructure. So first, it's very important to note that we are using, like anybody, unit tests, integration tests, manual testing, but we're also using an end-to-end infrastructure, which simply helps us to understand and figure out how are we behaving under load. So when we give service to our customers, we are not just deploying code and releasing it to production. We're firstly testing it, imitating the entire load, and watching ourselves handle that load. So with this system, we're able to raise up machines that are purely dedicated to to imitating a customer that is connecting to our browser, and after that, we are able to also deploy into that machine our jar client that is running a Selenium-based automation tool that is basically showing us a this green circle that some of you are testing streaming you're familiar with. Eventually, we have a report server that is containing all the reports, the screenshots, and all the issues that we have. It's important to say that once you are implementing your own autoscale service, this is mandatory, by the way. And the next slide is going to simply elaborate a bit more about our metrics and what we're testing on top of that. So imagine that right now I have a UI that is allowing me to raise 100 rooms with 10 participants inside those rooms. These are our virtual classrooms. So I can also deploy them in every region. I can also test China if I want to. But in every virtual classroom that we're testing, we're also testing these following metrics. We're testing the sent received bits per second of video and audio. We're also testing what is the packet loss percentage that we have, and a lot more metrics, as you can see right here. And this is also a picture of how it looks like when we're testing a video conference approach of our our virtual classroom. So this is the effort Neuro is basically investing in order to provide the best streaming and user experience to its end users. I would like also to talk a bit about the reactive implementation that we chose. We had a lot of options to take when picking the technologies, and we had a POC on Node.js, on Scala, where we also tested C++ implementation. It was just an overhead for a web service approach such as this. And we decided to simply go with the newest technology that is the most performable. We are planning in the future to also test approaches for implementing other components in the reactive. We're very pleased with the results and the performance. And That's it, guys. Thank you all for listening. Miteco Group, thanks for hosting this wonderful conference. And if you have any questions, you can either ask right now or ask me later if you'd like. Thank you very much.
Thanks, Ben. It's an impressive presentation on an impressive setup. Do we have any questions for Ben?
Hiya. Yeah, great presentation. Yeah, really
Thanks.
good. So you talked about sharing modules between microservices.
Mm-hmm.
How does this work from a testing perspective? So you're going to upgrade a module, maybe change something that's there, and then you have to run a set of tests against all services that use this module?
Okay, so that's a great question. First of all, our module composition also allows us to compose everything as a one big giant monolith, which is easier to test the entire stack in one shot. But note that this option for us to also be flexible for scaling away with every feature is giving us the ability to do that. So for example, I have a whiteboard service that's running in this specific region, and I have this huge load on whiteboard usage or any other usage on other components. So that gives me the ability to simply elastically scale out on a single component and not scale out my entire monolith like other products are basically doing that I saw personally. But the question for testing is surely, yeah, we're not doing that. We are end-to-end testing the system with when it's deployed fully. But once we are deploying code, we're also simply testing it as a giant monolith.
Okay, cool. Thanks.
Any more questions for Ben?
Okay. My first question is, can you describe more about the RTP forward cascading between multiple regions? Second question is, how come you need to implement your customized signaling server? Because as I know, Janus, it has its own signaling functionality. Yeah, thanks.
Okay, so the first question for cascading reasons, I said before, we have several business logic reasons. The most important of all of them is the threshold. So imagine that I have a Janus instance that is receiving streams that are published in it. Eventually, it's running on a 2-core machine as a Docker instance, and I have a limit of 700 streams. I have that limit because I load tested specifically one Janus and saw my stream quality gets pretty much degraded after I overreach that number. So this is the first reason why we're simply cascading, RTP forwarding those specific streams that exist inside that Janus instance, simply duplicating them to an empty instance, or better yet, an available instance. Also, we're cascading for webinar reasons because, see, we're hosting a 2,000 webinar online, and one Janus can have only 700 streams, only on that specific machine. Yes, if I'll go to a bigger machine, I'll have a bigger threshold. So we have to cascade also there. And also, the last reason is for lower latency, to get that ping down a bit, because you're connected with the public IP directly from, for example, China to the Janus in the United States. That's different when you're connecting to a Janus in China and using the backbone of AWS to get that stream all the way to the United States. So that's basically reducing the latency and improving the quality. Can you repeat the second question?
Okay. Second question is, why do you need to build your customized signaling server? Because Janus has its own signaling functionality.
Okay, so first of all, yeah, we are aware of that, but we're also aware of the fact that we need to manage the Janus instances from the outside of the Janus infrastructure itself. Better yet, every time you're connecting to a virtual class, you're also connected with a WebSocket connection to our signaling server, which is also running a lot of other business logic events. So for example, you're connecting directly to the virtual class, and you're also interested to either publish or not to publish. You're able to control whether or not you want to activate your camera. So basically, we had the need for our own personal signaling server to basically provide this specific business logic, and also we are programmers that like to develop code. So that's basically
Thanks.
the best reason I can give.
One more question from Anand.
Thank you. There was another guy with a microphone.
Hello.
Yes.
Nice presentation.
Thank you.
How do you manage your Docker containers?
Okay, so first of all, we're not taking what Kubernetes achieved. We are achieving that in a different way. So if I got your question correctly, our usage is simply to raise a 16-core machine on key regions, and this is how we're scaling out. Sometimes we're interested to test other approaches, but this is the best approach that we see so far. And on that machine, we're simply deploying a certain number of Dockers that are also treating the network bandwidth limit that you have on every instance, and CPU capacity, and a lot more.
Okay. How do you deploy Docker containers? So.
Okay, so this is
I mean, you use Ansible, you use other infrastructure as a code stuff, or what?
So the answer is yes, and we're also using more customized approaches of ours.
Okay, got it.
Yes, another question.
Okay, we had one last question by Anand here.
I just wanted to get a sense of what your bandwidth usage is on this 116-core server. Like, the bandwidth costs probably quickly add up. You're more bandwidth bound than your CPU bound, right?
Well, it's always the bandwidth limit that is your first threshold on the machine. The specific number of bandwidth that we have on that machine is a fixed bandwidth. Other machines are giving you up to somewhat bandwidth. So your better approach is to simply scale up with a fixed bandwidth machine that the cloud provider promises that bandwidth itself. Eventually, we had a different tries of testings of different machines, and we had this in mind that this actual bandwidth limit is going to have become the main problem in every EC2 machine or Azure machine or any other cloud providing machine. But this is a trial and error road that you can do it yourself. Some others are simply using all. You can basically use the cloud providers scaling out machine management and basically use Kubernetes to do that. And again, we did not develop Kubernetes from scratch or any wheel invention whatsoever.
Okay. How do you process the recordings and manage those after class?
Can you come again?
How do you process the recordings of class?
If I got the question correct, how do we manage the recordings of the class?
And process them.
Okay, so we have a cloud recording system that is basically approaching the room as another user that is an unseen user that is basically recording the entire screen, and we're simply keeping this this recording MP4 video format inside our cloud storage. Right after that, once a user wants to see that recording, he's simply accessing that file from our S3 bucket or any other cloud storage bucket.
Thanks, Ben. Let's give Ben another big round of applause. Thank you.